Hello, and welcome back. Today we are going to be further discussing momentum and collisions, and we are going to really dive into problem solving with these collision type problems. Now, as I go, I'm going to outline some of the sort of typical things I do, some helpful hints and tricks that work for me. But of course, as you go throughout problems, you're going to learn what works best for you. And I want to encourage you to really work with what's best for you. Now, let's take a look at this first collision problem. In this first collision problem, we have two train cars, and it's talking about how train cars are coupled together. That means how do we get two train cars to connect with each other so that they can move together. And it's going to be helpful when we define the collision, but that's a little bit into the future. I'm going to be very detailed here. So, as with any problem, I like to start out by getting a picture. I want to draw a physical representation of what is going on here. So in my physical representation, I start off by drawing two train cars. I know these two train cars are going to collide with one another. And I can figure out something about their mass and velocities from the problem, right? The one that has a positive velocity has a mass of 1.5, right? Well, which car is that? That's going to be car 1. The one with the positive velocity is moving to the right. And the one with the negative velocity I'm going to call car 2, and that's going to have the mass of 1.1 kilograms, right? And then we have our two train cars. They're going to be moving along a track, and eventually they're going to collide together. And then after they collide, they're going to be moving together as one. So this is really the before picture. I'm going to write an I there for initial. After they collide, well, they're going to be stuck together, and they're going to be moving together. And maybe they're moving to the right. Or perhaps, alternatively, they're moving to the left. I'm not exactly sure. And I can make a guess here based off of speeds and masses and stuff like that. But I'm not sure which direction they're going to move. I just know that they do have some final velocity. And since they're coupled together, I know that they're mechanically coupled together. They're connected. That means they're going to have the same velocity. That's going to, again, help us in a little bit. We go a little bit further and we start to examine this problem. Perhaps we want to take note of all of the different values in the problem. Keeping a chart of known and unknown values that are given in the problem can be incredibly helpful. So let's go ahead and write out our known values. We have this 1.5 times 10 to the 5 kilogram mass. That will tell me the mass of one of my cars. Okay, well, hold on now. We have two cars. We have two cars with two different masses, so it can be helpful to differentiate those. And I will use M with a subscript of 1 to represent the mass of the left car, the car that I labeled as 1. And the mass of car 1 is going to be that 1.5 times 10 to the 5 kilograms. So I write it down. I know it's up in the problem. I know I could always refer back to it, but having this table really helps clean and organize everything that I got going on. Like the mass for car 1, we also are given the mass for car 2. So I'm going to use M with the subscript 2. I'm going to use subscript 2 for any quantity that's related to the second train car. And here I have 1.10 times 10 to the 5 kilograms for my mass. Okay. We continue to look at the problem, and it also gives us velocities, right? It gives us both the magnitude, the 0.3 meters per second. It also gives us the direction, positive or negative I hat. So we have the complete full initial velocities. And I'm going to write down V1 for the velocity of car 1. And I'm going to put a subscript I there to represent the initial case, as opposed to F, which we will use for final, meaning after the collision. I is before the collision, F is after the collision. So your initial velocity of car 1 is going to be positive 0.3 meters per second in the I hat direction. And then we go on and we look at the other car, and we are given the other velocity, and it's given as a negative, meaning we have direction, we have magnitude, we have the complete second velocity, which is negative 0.12 meters per second I hat. And I hear you screaming through your computer that I see my mistake too. It wasn't 3.0, it was 0.3 meters per second I had, so made that correction. So we take a look at this, and we have our initial values. We don't know their final velocities. We do know their masses aren't going to change, right? The cars are not offloading any mass or anything like that. So this is all we have for the moment. We continue to look at this and we say, okay, well, now I need to define my system. When you're doing conservation problems, a well-defined system is an absolute must. How do we define our systems, though? Well, we can define our systems by first making an interaction diagram. And I know this is a pain, but we make our interaction diagrams to be very clear about what values are what. So here our interaction diagram is going to have car 1, I'm going to use C1 for car 1, and car 2, C2 for car 2. And I know during the collision that these two cars are going to interact. Car 1 is going to push on car 2, car 2 is going to push on car 1. So during the collision, they're going to interact. So I'll put this red line in there to represent our collision interaction, which is only occurring during the collision, right? We have some other objects in our system, right? We have the rail that each of the cars are gliding on. We also have the entire Earth. And we can link those, and I'll put links to those. We have normal force between the rail and the cars. We have gravity between our entire Earth and the cars, so I'll put those in there as well. Now, it's important to know that unless otherwise stated, friction is going to be negligible in this class. There is going to be a little friction in this problem, but here we're going to neglect friction. I explained why friction is pretty negligible in a previous problem, but again, here, friction negligible. We're not going to worry about it. And then we seek to answer the question that I asked earlier. What is our system? How are we going to define it? And there are two important factors here, right? Whenever you're defining a system, you want it to be closed, and that means 1, that the mass does not change, and 2, that the external net force is going to be 0. So we look at our problem and we say, okay, well, how am I going to describe my closed system? Perhaps we look at car 1, right? We say car 1 is my system. When we do that, we see that the gravitational and the normal force, these are two forces that cross the boundary from environment to system, meaning these are external forces. But these two external forces are going to cancel themselves out. So between these two forces, no net external force, but that leaves this collision interaction, and the collision interaction is going to be a net external force if we define our system to be car 1. So this is no good. This doesn't work. This is not a closed system. So we back up and we say, okay, well, what other system can we define? Maybe car 2. Maybe car 2 will work. Car 1 didn't, but maybe car 2. Normal and gravity, those will cancel each other out again, but that leaves us with this leftover force giving us an external force, meaning this also is not a closed system. So we back off of that, and then we maybe define car 1 and car 2 to be our system. If we take both of these to be our system, well, that's wonderful. Our mass doesn't change. Our car 1 and our car 2 stay the same mass. And the normal forces and the gravities will cancel each other out as well. So no net external force. So this that I've circled here in the green, taking into account both cars together, that gives us a closed system. And in order to utilize this closed system, we understand that momentum initial is going to equal momentum final, as is the case with any closed system. But what that really means is that the initial momentum of car 1 plus the initial momentum of car 2 is going to equal the final momentum of car 1. Nope, that's not how I was doing my subscript. Momentum of car 1's after the collision and the momentum of car 2 after the collision. So again, I'm sticking with the subscripts. A 2 will mean car 2, a 1 means car 1, I means before the collision, F means after the collision. So I take all of this and then I start to think about what type of collision is here, because the type of collision is important. In this case, we have two cars that are coming together and they are going to stick together. That gives us an elastic collision. No, not an elastic. An inelastic collision. Inelastic collisions are the type of collisions where two things stick together. And what's important about inelastic collisions? Well, they'll have the same final velocity, same magnitude, and same direction. So we have our two cars colliding with each other, ending with the same velocity. And what that means is that our initial momentum of car 1, let me rewrite that. Our initial momentum of car 1, when we add it to the initial momentum of car 2, that is going to equal M1V final. And I don't need to bother putting a 1 subscript or a 2 subscript here, because car 1 and car 2 have the same final velocity. So there's no point in putting a 1 or 2 on the final velocities. They're the same value, whatever that value might be. We take this and we say, okay, well, I know what the masses are. I know what my initial velocities are. The only unknown here is my final velocity. So I take this and I solve for the final velocity. And what you would get is that the final velocity is going to be m1 v1 initial plus m2 v2 initial divided by m1 plus m2. Make sure you can do the algebra to find this value. And once you plug things in, you'll find the final velocity is going to be a positive 0.122 meters per second. But if we look at our sig figs, 2 sig figs, so really how we should write our final velocity, the full vector velocity, as positive 0.12 meters per second in the I-hat direction, meaning it ends moving to the right. And in fact, I could have guessed that initially the car that is moving to the right had the larger momentum, and that's going to overwhelm the smaller momentum, meaning they both move to the right afterwards. So you can make an educated guess that that was going to be the case, but here is the proof, the mathematical proof of the final velocity. So then we take a look at another type of collision, right? There are 3 types of collisions. The next type of collision is going to be of this type of problem that I'm giving you, and we're going to read through the problem and define the collision in a moment. So here we have a 20-kilogram child holding onto a 2-kilogram ball, and while he is doing so, he is coasting in a 3-kilogram wagon at a speed of 3 meters per second. While the child is rolling along in this wagon, he is going to toss the ball out backwards at 2.5 meters per second. The question is, what is the final speed of the child? So, drawing a picture. Again, I recommend drawing pictures. Here's my wagon. Child is going to be in the wagon, and the wagon is going to be moving to the right. Initially, the child has the ball. So everything is moving to the right at 3 meters per second. This is our initial case before the collision. And after the collision, the child is going to be rolling along in the wagon still, but the child will have thrown the ball backwards. So we have after the collision, our child moves forward in the wagon, the ball moves backwards. And I did intend for this to be 2.5 meters per second with respect to the ground. So we have that V2 final being 2 meters per second. Again, we'll define all of those values in just a moment. When we take a look at this, we might be tempted to initially begin with the question of what type of collision this is. Right? We don't have to solve things in the exact order that I did the previous problem. This time, let's take a little bit of a different approach. Here we ask the question, what type of collision is this? We have initially all of our objects together moving with some speed, and afterwards will our objects separate. As they separate, we consider the type of collisions, and we come to understand that this type of collision is considered an explosion. No, it doesn't have any sort of chemical release of explosive powder or whatever, but this still is considered an explosion type of interaction. So we know that it's an explosion interaction, meaning that if we could define our system well, then we know that the momentum must be conserved, and it should be of the form that the total mass times the initial velocity is equal to the mass, nope, didn't want to put an either. The mass of one of our objects in the collision times the velocity final of that object. And then we add to that m2 v2 final, right? This is the equation that we derived for our explosion type collisions. Now, we analyze the physics, we analyze the concepts first, and sometimes doing this has an advantage because now we know the different quantities that we need to fill. And in fact, we can begin to think about what object is what, right? And here we want to define our closed system. Our closed system is going to be all of our objects together. But this closed system is going to be a combination now, not just of one object, but three objects, right? The car, or not the car, the wagon, the child, and the ball. So we look at this and, well, maybe we need to make a change, right? These momentum equations, they are very useful because we can add to them. We know that total momentum is conserved, so all we have to do is m3v3 final. So why do we do this? We do this because now we have this understanding that all of our masses, when we take all of these objects into consideration, all of them are in our system, meaning that we have some conserved values. So where do we go from here? Well, from here, what we want to do is define our quantities, right? We still want to be able to list out our known and our unknown values. And what I'm going to do is be very specific about which object is which. So we have three objects, 1, 2, and 3. For object 1, I am going to say object 1 is going to be the child. For object 2 is going to be the wagon. And for object 3 is going to be the ball. I make this little key here so that I will always remember which object is which. When we start to deal with many objects, it can get confusing on what are we calling 1, 2, or 3. Alternatively, we could have written MC for child. Perhaps we wanted to take this convention. MB for ball. And M was the third thing, wagon, or W for wagon. We could choose whatever naming convention works for us. But for me, I'm going to keep things general. I'm going to use 1, 2, and 3 as my examples. Okay. So what values do we have now? We have the mass of the child, M1, and that's going to be 20.0 kilograms. We have the mass of the wagon. The mass of the wagon is going to be that 3.0 kilograms. And we have the mass of the ball. I already messed up my convention. M3 is the mass of the ball. Let me fix this. M2. M3 is going to be the mass of the ball, which is 2 kilograms. All right, so we have our wagon, our child, and our ball. Wonderful. We then look at this and we say, well, that's not all of the information we need, right? We also need to know the initial velocity, and since everything is moving together, we know that the initial velocity is the same for each, 3.3 meters per second. So I'm not going to bother putting subscripts 1, 2, or 3 there because they all have the same initial velocity. And we can look for the mass total that is appearing in our equation. And since it's appearing in our equation, maybe we care to write it down. And the total mass here is going to be 25 kilograms. Nope, not 25.00, just 25.0 kilograms, right? Let's pay attention to our sig figs. So we have all of these values. We look back to our equation. We say, okay, well, in our equation, we are actually given one more piece of information. We're given the third object, the ball's final velocity, which is going to be negative 2.5 meters per second in the I hat direction. All right, so that concludes our list of known values. So what did I do here? I drew out a picture, I defined my system, and I wrote out my equation that applies to our explosion objects. The question of what is our final velocity? Well, looking at this, we still have the child and the wagon being mechanically connected, so V2 final is equal to V1 final. And with this until we can take our two equations with our two unknowns and solve it, and what we would find is that the final velocity is about 3.8 meters per second. I'm going to leave that for you to do at home. Just to check your math though, you should get 3.8 meters per second as the final velocity for our child and the final velocity for our wagon. Again, they should have the same final velocity. All right, and then we move on to a third problem. And this third problem, well, we saw inelastic, we saw explosion, so that must mean this one's elastic. And I saved this one for last because it's probably the hardest one. Although it's only hard because it involves two conservation laws. You see, when we take perfectly elastic collisions, we generally assume that there's no energy loss. Now, in reality, there are going to be energy losses. But in this case, we're going to assume no energy loss. For this problem, we have two bumper cars that are going to bump into each other. One car is going to rear end the other. And drawing a picture out here, we have our two bumper cars. We'll call this bumper car 1 and bumper car 2. Our two bumper cars are going to collide into each other, meaning that initially it's going to be a rear end collision, meaning initially they travel in the same direction, and they are going to collide into each other and then continue to move forward. We define our system. Our system is going to be our two cars, right? It's going to be the objects colliding. I'm going to skip a couple of steps here just to sort of speed things up. But it's the same process that we've done in the last ones. And then we think about the physics that's involved, and the physics that's involved is that the momentum initial is going to equal the momentum final, as well as the kinetic energy being conserved. Your initial kinetic energy is equal to your final kinetic energy. But what does that mean? What does that mean? That means whatever quantity you calculate for your initial momentum, which is mass times velocity, whatever value you calculate for your initial momentum is going to be the same as the quantity that you calculate for your final momentum. Same is going to be true for your kinetic energy. So with this problem, we have these two conservation laws, and that's going to be important because, as we'll see in a moment, these two equations will have two unknowns, and it becomes an algebra problem to solve. So let's start with our conservation of momentum. Conservation of momentum says that our initial momentum of car 1, when we add it to our initial momentum of car 2, that is going to equal our final momentum of car 1 and our final momentum of car 2. And here we don't have our objects mechanically linked at any point. They're not combined together. They're not moving as one. So our initial velocities and our final velocities, they're all going to be different values from each other. So we start off with this equation. And this actually simplifies quite a great deal, because our carts, they're identical. What does that mean that they're identical? That means that they have the same 400 gram mass, meaning that we can divide both sides by the 400 kgs. And mass 1 is 400 kg, mass 2 is 400 kg, meaning that our masses totally cancel out, giving us the equation that our initial velocity of car 1 plus the initial velocity of car 2 is equal to the final velocity of car 1 plus the final velocity of car 2. And this gives us one of our two equations. Well, what's the other equation? The other equation comes from conservation of kinetic energy, which we start off with 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared is equal to the final kinetic energy of car 1 and the final kinetic energy of car 2. Long equation. Now this equation is always true, is always true with perfectly elastic collision, but the nice thing is these 1/2s, well, it's in every single term. So the 1/2s actually cancel out, meaning we have m1 v1 initial squared plus m2 v2 initial squared is equal to m1 v1 final squared plus m2 v2 final squared. But likewise with the momentum equation, our masses all cancel out here. So we rewrite this, and I'm going to rewrite it up here, that v1 initial squared is plus v2 initial squared is equal to v1 final squared plus v2 final squared. So we have our two equations here. We have two equations, and with our two equations, we actually have two unknowns. So that means we have to solve this. We have to solve these two equations with two unknowns. How do we do that? Well, the first thing we can do is take this momentum equation and solve it for v1 final. We could also solve it for v2 final if we'd like, but I'm going to solve it for v1 final. v1 final is going to be v1 initial plus v2 initial minus v2 final. So we have this relationship that if we had v2 final, we could plug it in and find v1 final. And taking this equation, plugging it in to our conservation of energy equation, we have v1 initial squared plus v2 initial squared is equal to v1 final squared, but instead of writing v1 final squared, I'm going to write v1 initial plus v2 initial minus v2 final quantity squared, right? So I'm just substituting in v1 final squared. We add that to v2 final quantity squared. We take a look at this, and now we have to start expanding. This is going to be a little bit messy, so I'm going to clean up a little of the space down here, erase my conservation of energy equation, but I'll keep my momentum equation. So what we're going to do is we're going to expand out this exponent. So how does that expand out? Well, we have on the right hand side v1 initial squared plus v2 initial squared, and that's going to equal, I'm going to split this into being, I'm going to rewrite this before I multiply in the squared. I'm going to rewrite this as v1 initial plus v2 initial minus v2 final. And all I've done here is put in a parenthesis. I put in a parenthesis here to make this next step a little bit more obvious. Because now when we do the distributing in the square, well, it becomes a little bit more obvious what this next step looks like. v2 initial quantity squared is going to be equal to v1 initial plus v2 initial squared plus v2 final squared minus 2 times v1 initial plus v2 initial v2 final. And then we add to that the v2 final squared. Okay, so that's a lot. That's going to be something we want to further expand upon. But it is important to remember, right now I'm going to outline these values, this value right here, as well as these values. Well, they're all just numbers. That's all they are. So we could plug in at this point. I'm not going to. I'm going to do the algebra a little bit more. But we could plug in the numbers at this point. And that would give us an equation that's pretty easily solvable for v2 final. But I'm going to take another step before I do that. This next step I'm going to do is take this squared and now distribute it into that part of the exponent. And when I do that, I'm going to need even a little bit more room here, so I'm going to start to erase some of these earlier equations. So v1 initial squared plus v2 initial squared, same thing on the left-hand side of the equation, that doesn't change. And that's going to equal v1 initial squared plus v2 initial squared plus 2 v1 initial v2 initial, right? And that's coming from this distributing the exponent in. And then we add to that v2 final squared, and then we have minus 2 v1 initial plus v2 initial, v2 final plus v2 final squared. Yes, this is getting messy, and these elastic collision problems can be a bit tedious algebraically. But if you just follow it through step by step, things start to simplify. For example, we have v1 initial squared on both sides. We have v2 initial squared on both sides. So what does that mean? We have 0 is equal to, I didn't mean to put this in red. That canceled out. There we go. So what do we have here? We have 0 is equal to 2 v1 initial, v2 initial. And I'm going to rearrange things a little bit. Minus 2 parentheses. 2 v1 initial plus v2 initial, coming from this term over here. And then we add to that v2 final quantity squared, and then I missed a v2 final there, so let me backtrack and correct. v2 final plus v2 final squared. And you look at this, and maybe it's not obvious yet, but this is a number. This part of that term is a number. This ends up just being a quadratic. And in fact, you plug in the numbers now. If you plug in the numbers for your initial velocities, what you would find is that 0 is equal to 64.8. Almost put my decimal in the wrong place. 64.8 meters squared per second squared minus 22.8 meters per second multiplied by v2 final plus v2 final squared. And you take this, you plug it in, you solve the quadratic, and when you solve the quadratic, what you'll end up seeing is that v2 final is equal to 6.00 meters per second. v1 final is equal to 5.40 when you plug it into an earlier equation, 5.40 meters per second. This quadratic actually has two solutions. One of the solutions is not physically possible. This is the physically possible solution, where you have them swapping velocities. Now you ask the question, do they always swap the velocities? And the answer is no. This only occurs when they swap velocities. That only occurs when two Identical objects collide with each other. If they are not identical, then they do not collide. Then they do not swap velocity, sorry. And if I wanted to be very correct here, I would put in a directionality and say these are the velocity vectors. Okay. So a lot there. I know this is a little bit longer of a video, but it involves quite a bit more problem solving, and I, tried to start off doing like step by step, and I tried to show you the algebra all the way through. If you have any questions, please be sure to ask. Otherwise, I will see you guys in the next video.